Thank you, Jan. Hey, everyone. My name is Mehdi Khanzadeh. I'm an associate professor at Temple. First of all, I would like to thank my PhD student who worked on this, Abdullah. So he's done the hard part of the job. So first of all, what is motivation for our study? So I in the previous presentation kind of touched upon this. We have higher binder content, which impacts the sustainability aspect of the 3D printing as well as the cost part of it, right? So that's the main motivation, and we approach that with using two different perspectives. One, use of the cellulose nanomaterial, which are green natural materials to help with the fresh and hardened properties of the 3D printed system. The other aspect of our study was on the binder type, so how we can implement 3D printing in the low zero clinker binder. Moving forward, I'm going to discuss what exactly I mean by binder type. So a little bit of a background on the cellulose nanomaterials for those of you who are not familiar with this material. So mainly in this study, we use the CNC cellulose nanocrystals. So those are crystalline part of the polymers extracted from the trees, plants, or other sources. So they are sub-micron scale in length, less than 0.5 micron, and the other properties are listed. So it comes in two forms. You can have it in dry form, powder form, or you can have it in emulsion base, which is shown at the right bottom figure. We typically use that one because that helps with the dispersion. The other form is the cellulose nanofibers. So these are in a micron scale, about 1 to 5 micron with a high surface area. This is another type of the popular cellulose nanomaterial used in concrete. As far as the binder goes, so I'm going to today discuss two different types of the binder we tested. One is the alkali activated binders in comparison with the OPC system. The other one is carbonatable binders. So I'm going to stick to more discuss the fresh properties, which is the focus of this session, but I think we have to also discuss what is the structure property relationship for this binder. At the end, the performance is important. So the first part, I'm going to cover the alkali activated. This is a paper published, so if you want to get more details on that, you can scan that QR code. As far as the printing setup, we used the bench scale extrusion-based printer. So we did a lot of modification on a clay-based printer, so to make it more intuitive for cementitious material. Basically automatic retraction of our piston, and also we have a two-part, so we can take the bottom part more as a plugin. So add material, consolidate, and right away to put it back, and we kind of improve the open time for our print. As far as the geometry goes, we adopted very simple geometry shown here. So we have outer layers in a straight line, and then the infill, we use a more zigzag pattern that is shown here. So we wanted to extract some samples from this to our mechanical test, and that was the main purpose of that. So printability criteria, as most of the researchers do, we also did some visual inspection, the stacking, number of the layers we can stack, and all that. But as we all engineers, we love to quantify stuff, right? So that's why we adopted this setup shown at the top right. Basically, it's a very simple syringe-based system. We mimic exactly the print speed we have in the printer. So this gives us more basically quick way of the screening the mixes to get to answer or to optimize our system. The example of the results from this test setup shown at the bottom right. So the most important part we focus is the steady state part. So we look at the extrusion pressure, we look at the smoothness of the graph, and also the gradient of the graph. So this is the way basically we try to, again, screen our mix and get to the optimum point as soon as possible. So as far as the mix design, we had, again, alkali activated system and OPC system for comparison. We had control without CNC, and then 3 different dosage of the CNC for these 2 systems. So for alkali activated, we used a combination of the fly ash class F and slag. So that's the percentage. Later on, I'm going to discuss how we got to that point. We use a sodium hydroxide, sodium silicate combination for activator. Again, we're going to discuss how we get the optimum dose. And for the CNC, we use the aqueous form, about 11% solid content. So this is just a simple overview, how we kind of screen using this simple method. So at the left side, you are seeing non-printable example. At the right side, you are seeing a printable example. And then we can test basically what is the impact from the CNC, what is the impact from different admixture, and so on, right? So we are trying to develop basically, again, area that is optimized, and we can try to focus on that area and work on the mechanical performance. So I'm going to more discuss that in coming slides. So one observation we had as far as the comparison between alkali activated and OPC was the required liquid to binder ratio for printing. So for alkali activated, we needed a higher liquid to binder ratio, and that liquid contains all the admixtures we have in the system plus the water and activator. So, but in OPC, we go with, or we can go have a printable system with the lower liquid to binder ratio. The other observation we had is when the CNC content increases, basically what you are seeing in the x-axis here, in OPC, the change is more dramatic to get the printable system for the liquid to binder ratio compared to the alkali activated system. So in case of the OPC, when we compare these graphs from the, again, syringe test, we didn't see much difference, a little increase in some cases when we increased the CNC content. But interesting observation we had in case of the alkali activated binders. We saw a decrease in the extrusion pressure, better print quality when we use the CNC with different content for alkali activated. So the observation was that this CNC works as a more VMA, viscous modifying agent, so that can help to reduce part of your chemical admixtures in this case. So again, going back to this graph, to get to that optimum point, we had the x-axis basically different combination of our activator, the y-axis different combination of the binder, basically slag and fly ash. So using that method I mentioned, we tried, again, different proportions. And in some cases, you see we needed a retarder or different type of admixture to get to the printability. In some cases, it was a printable, but the strength was low. So finally, we get to the point that in that area, we were able, basically, that green dot, to get to the optimum point that we get both good fresh properties or printability and hardened properties. So looking at some of the mechanical performance, at the left side, you're seeing this result for the modulus of the rupture. So the blue one, basically our OPC system, the green one is alkali activated. So for OPC, we use 28 days of wet curing, but for alkali activated, we adopted 2 different approaches for the curing. The first one, sealed curing, and the second one, heat curing for 7 days at 60 C. So the observation we had, if you look at just the CNC content, when we increase the CNC content, up to some point we see some improvement, but after a certain concentration, we see a drop in our basically performance. So basically, that's connected to, again, that dispersion quality in the system. So about 0.5 to 1% CNC content, we saw the optimum concentration for this application. The other observation we can have from here is the comparison between heat-cured and sealed-cured system. While sealed-cured alkali activated is up to certain concentration provides similar performance to OPC, but when we use the heat curing, it's even performed better than OPC. So that's the, I'm going to have more slide on why that's the reason. We looked at the relationship between the modulus of the rupture and strengths, and we compared with the ACI recommendation, ACI 318 and 353. So you see that most of them above the ACI 318, and in case of the heat cure, that's the best performance or more ductile system we observed. We did a lot of testing on the CNF. We haven't published this work, so I'm not covering a lot of it, but even with 0.1% CNF, we reached a much higher, basically an OPC system performance compared to CNC. But as far as the fresh properties or printability, didn't contribute much versus the CNC that acted more as a VMA. We looked at the porosity. So there's a linear correlation between porosity and strength. You can see that. And also we looked at some of the permeability criteria using the electrical resistivity. There's no impact from CNC dosage much, but the alkali activated shows higher electrical resistivity compared to OPC. One interesting observation we had for the CNC system in an OPC case, when we looked at the degree of hydration or the bond water in the inner part of the 3D printed material, we saw an improvement in the degree of hydration or the bond water or the reaction. And this is basically gives an indication that the CNC act as an internal curing agent in this case. And this is a good advantage for 3D printing, right? So we discussed, the previous presenter discussed about the curing importance. So because of the low permeability, the external curing we do is not going to do the job. So if we can have this benefit from the CNC, it can basically improve the performance or the degree of hydration in the inner part and help with the controlling the cracking and the performance. This is more basically data from the TGA. I'm just going to skip that. We looked at the microstructure for alkali activated sealed versus the heat cured. The left side is the sealed cured, right side is the heat cured. So our observation is this is basically samples taken after the modulus of rupture experiment, right? So we see a lot of crack distribution in the sealed cure versus the heat cure, which makes sense because we get low strength, right? But the main reason is because of a lot of unreacted fly ash and also slag in the sealed cure one versus the heat cure one, which dissolution rate is higher, so it improves the microstructure in general. This is more images. Again, as I said, more unreacted materials in case of the sealed cure versus the heat cured, which we have more reaction products in either NaSH or CNash or calcium aluminate silicate hydrate. We also done some with our collaborated at University of Wisconsin, some techno-economic analysis and some environmental impact on OPC part, with and without CNC. That's the paper published on this topic, so I'm not going to spend a lot of time, but something I wanted to discuss is if we just consider mass or volume as our functional unit, use of the CNC a little increases the environmental impact as well as the cost for our system, for 3D printed system. But if we consider the other units such as the performance unit, flexural or compressive strain, in that case we see a lower minimum selling price and a lower environmental impact when we use the CNC. And there are different factors contributes to this because we don't have a lot of mass production of the CNC to optimize that process and the transport part, and so it's a pretty new technology, so it's going to take time to get to that point. So the second part is a couple of slides on the carbonatable binders that I'm going to discuss. Is this paper again published? You can download the paper for more details. So the idea and motivation behind this, we said right now it's kind of popular use of different carbonatable binders, low-rank calcium silicates, a slag system for CO2 curing. So we want to see these two new technologies, 3D printing and carbonatable binder, how they work in combination, right? So is there a chance to 3D print this type of the binders for CO2 curing purpose? So we developed the ternary mixers for these carbonatable binders. So we use three different basically binders, wollastonite, hydrated lime, and either OPC or slag to give us that initial stiffness in the mix. So those are the basically optimum point we reached based on the previous experiment I mentioned, alkali activated part. So we get to the 55% wollastonite, 15% hydrated lime, and the remaining 30% is either OPC or slag. So we had this system with and without CNC to see the impact from the CNC, either on the fresh properties or hardened properties. So one observation we had, if you want to limit the amount of admixture you use for this type of the binders, you have to increase your water binder ratio. So in the OPC case, we use 0.26 typically. So for the this binder, we use 0.42. We recently developed even 0.3 and 0.26 for the carbonatable binders, but again, the requirement for admixture and admixture type is different, so you have to work on that. It's not that simple. So for OPC, we use the water curing for 14 days. For other binders, we use the CO2 curing at 20% concentration to mimic the flue gas concentration, and after 14 days, we basically tested them. If you look at that, again, results, the extrusion pressure results. At the left side, you see the impact from the water binder. So how by increase the water binder, we get to the point that it's printable. So you have, again, better print quality. One observation we have overall from this study is if you keep that pressure under 100 Newton, it's typically printable system. At the right side, you see the impact from the CNC for this carbonatable binder. So we see a slight improvement by use of the CNC. Again, that you know, the VMA functionality of the CNCs is playing a role here as well. As far as the mechanical performance, we've done a lot of testing on this, but I'm just going to limit it to this slide. Again, in the paper, we have all those discussions. So this is a flexural or the amounts of the rupture measurement. So if you compare here the OPC, which is lower water binder, 0.26, with the carbonatable binder, which is high water cement ratio system, the control one without CNC performs about the same after 14 days CO2 curing. But by addition of the CNC, we see about 25% increase in the performance or the basic amounts of the rupture measurement. So CNC again improves the mechanical performance in addition to the fresh properties or printability discussion we had. We've done environmental impact analysis on this one as well. If you look at the graph, the right side is material side or comparison between this, different mixer we have. The left side is the CO2 sequestration or CO2 curing, the CO2 that we absorb into the system. So if you compare the material section, you see that, or CO2 emission from the material. So all the CCM system is still less CO2 intensive compared to the control one, OPC. Obviously, slag one performs better. Again, if you add the CNC compared to without CNC, we have a small increase there. But overall, if you look at the both curing process and the material side of it, we see 40 to 60% reduction in the CO2 emission for OPC and slag system. So some conclusion from the first part of the study on alkali activated material. So as I said, we see a really good improvement on the fresh properties or printability, act as a viscous modifying agent, use of the CNC. And we see the improvement up to 0.5 to 1% of the CNC on the mechanical performance. And we believe, and we showed the study that these can be alkali activated CNC combination can be sustainable at the same time, good performance for 3D printing. For second part of this study, as I said, it slightly improves the printability use of the CNC, but we see a lot of good increase or high increase of the performance in case of the flexural strengths. And as I showed, from the CO2 perspective, it reduces the 40 to 60% CO2 emission. But as I said, we are still working on this topic to reduce the water binder for this CCM, and we are hoping to get much higher performance. With that, I would like to acknowledge our funding sources that are listed here. My student that they are doing the hard part of the job. I'm doing the easy part. And thank you for your attention. Happy to answer any question.